Predicate logic lets us formulate quite general statements and questions about our domains of interest. And to express statements in predicate logic, we use formulas. And formulas are defined inductively. They are built from terms, predicate symbols, negation, binary connectives, such as disjunction and conjunction, and quantifiers. Terms are also defined inductively. Variables and constant symbols are terms, and we can use function symbols to build more complex terms, where the arguments are again terms. For example, f of x and y is a term. F is a function symbol, and the arguments x and y are variables. As another example, s of 0 is also a term. A predicate has a name and a number of arguments. The name is called a predicate symbol, and the number of arguments is called the arity of the predicate. And by convention, predicate symbols in predicate logic typically start with an uppercase letter. That's in contrast to Prolog, where predicate names typically start with a lowercase letter. For example, P is a predicate symbol, and Q is a predicate symbol. And predicates allow us to make statements about properties that domain elements have, and how they are related to other domain elements. And in first-order predicate logic, we can use universal and existential quantifiers that range over domain elements. And in second and higher order logics, we can quantify over predicates, relations between predicates, and so on. For example, in first-order predicate logic, we can express for all x, p of x holds, where x ranges over domain elements. So these are the syntactic components of formulas. And to assign meaning to these constructs, we must define their semantics. So we would like to assign to each statement one of the truth values, true or false. And this is done by specifying an interpretation. An interpretation defines a non-empty set D, which is the domain of discourse, and a function I mapping function symbols to functions and predicate symbols to relations over the domain of discourse. So, depending on the interpretation, a predicate is either true or false for any concrete arguments. And the point is that we can define what each predicate means by stating what holds about each predicate. A formula is satisfiable if there is an interpretation under which it is true, and such an interpretation is called a model of the formula. And a formula is valid if it is true under all interpretations. And the notion of semantic consequence relates formulas according to semantic properties. B is a semantic consequence of A if B is true in all models of A, that is, in all interpretations that make A true. So this is a semantic definition of a logical consequence relation, because it refers to the meaning of formulas. Now, let's consider a few examples of formulas. Let's use the predicate M to state that a particular element from our domain of interest is mortal. We write M of C to state M holds for a concrete domain element, indicated by the constant symbol C. And M has arity 1 because it has one argument. And of course, whether this is true or false depends on the interpretation. For example, for this concrete formula, there are interpretations that make it true, so the formula is satisfiable, and there are also interpretations that make it false, so the formula is not valid. We can use the quantifier for all to express the statement that every element from our domain of interest is mortal. This is called a sentence in predicate logic, because all variables that occur are quantified. So in this case, x is the only variable that occurs, and it is universally quantified. And again, the truth value of this sentence depends on the interpretation. So there are interpretations where the sentence is true, and also interpretations where it is false. And in any case, everything is mortal is one statement that we can in principle express in the language of predicate logic. And a statement we make can of course be too general. For example, we may want to reason about immortal entities too, and characteristically immortal entities are not mortal. So to gain some experience with how various statements can be expressed in first-order logic, let's change the statement to every person is mortal. So let's use the predicate P of x to denote that x is a person. So we must relate the predicates M and P using logical connectives to express that every person is mortal. And a bit of reflection tells us that we can use logical implication to state for all x, if x is a person, then x is mortal. So for all x, P of x implies M of x. Okay? And there are of course also other equivalent ways to express this statement in first order logic. For example, we could equivalently say that there is no person that is immortal. So there is no x such that P of x holds, and at the same time M of x doesn't hold. So we have now seen a few specific examples of statements we can formulate using sentences in predicate logic. And in these examples, we've only considered unary predicates, that is, predicates with only one argument. However, a predicate may of course also take more than one argument, and in that case, the predicate expresses a relation between its arguments. For example, we could use the predicate smaller of x and y to mean that x is smaller than y, and we could write such a predicate equivalently in infix notation as x smaller y. So this is simply a syntactic variation. As another example, we could use a predicate like P of x and y to denote that x is a parent of the child y. And we could use a predicate like A of x and y to state that x is an ancestor of y. Or use equals to denote equality. And use a predicate that is true if z is the sum of x and y, and so on. And a major attraction of predicate logic is that we can use it to define many important concepts, and we can then reason about them and derive logical consequences. And we can do this by defining a theory. And we use the word theory quite liberally, so a theory is simply a set of sentences. And the sentences of a theory are called theorems. And a common way to specify a theory is to state a set of sentences that are called axioms. And axioms aren't necessarily something that's intuitively true about the objects we want to describe. And the axioms are normally also not valid sentences. So they are generally not true in all interpretations. Rather, think of axioms in this sense as constraints that help us specify the essential properties of the things we are interested in. Axioms in this sense are also called assumptions, postulates, or non-logical axioms. For example, we can use first-order predicate logic to express what we mean with a set. And that's good, because we have now already mentioned set a few times. So what is a set? And a popular way to specify sets is Zermelo-Fraenkel set theory, abbreviated as ZF, and also ZFC, that is ZF with the axiom of choice. The axioms of this theory are, for example, the axiom of extensionality, that is, if two sets have the same elements, then they are equal. So formally, for all x and for all y, if it is the case that for all z, z is an element of x if and only if z is an element of y, then x and y are equal. Then the axiom of regularity. Every non-empty set x contains a member y such that x and y are disjoint sets. And again, we can express this with a sentence. We can also express what we mean with a subset. A set Z is a subset of a set X if and only if every element of Z is also an element of X. As another example, the axiom of power set states that for every set X, there is a set Y that contains every subset of X, and so on. And on the understanding that all semantic consequences of these axioms are also part of the theory. This is called a deductive theory because it is closed under the consequence relation. Now, suppose we manage to state the key properties we want to express about sets in the language of predicate logic. Then a few questions arise. For example, is the theory consistent? That is, does the conjunction of these sentences have a model? Or have we, for example, accidentally imposed conflicting requirements? So this is a semantic view of consistency, which is therefore also called semantic consistency. And if you recall, for this property, we can also use the word satisfiability. So a theory is semantically consistent if it is satisfiable, that is, if it has a model. There is also a syntactic view of consistency. Syntactic consistency of a theory means that for all sentences of the language, the theory doesn't contain the sentence and also the negation of the sentence. So for all sentences phi, either phi is not in the theory or the negation of phi is not in the theory. And importantly, one can show that for first-order theories with a well-orderable language, the semantic notion of consistency coincides with the syntactic notion. Because if such a theory is syntactically consistent, then it has a model. This is called the model existence theorem, or rather, the model existence theorem, as the most important and most well-known instance of several model existence theorems. And for instance, ZF and also ZFC are examples of such theories, because they are first-order theories with a countable and therefore also well-orderable language. So the model existence theorem is an important link between syntax and semantics of a theory, that is, between sentences and their meaning. And notably, this connection breaks down for second and higher order logics, where a theory can be syntactically consistent yet not have a model. And this concrete theory, ZF, is widely believed to be consistent. However, it's not known to be consistent. What is known, though, is that many important statements are independent of ZF. A statement is independent if neither the statement nor its negation are theorems. For example, in 1938, Kurt Gödel proved that if ZF is consistent, then ZF plus the axiom of choice is also consistent. And in 1963, Paul Cohen used a then new and groundbreaking technique called forcing to show that if ZF is consistent, then so is ZF plus the negation of the axiom of choice. So we can't accept or reject independent statements by appealing to the existing axioms. And if we want to settle such questions, we may have to add new axioms or look for better axioms that capture more properties of sets. A closely related question is, of course, what the semantic consequences of these axioms are, and also to check whether a given formula is in fact a theorem of, for example, set theory. And also, how do we even determine semantic consequences? It's not clear how to do this, because there are infinitely many possible interpretations, even uncountably many. So we can't simply try all interpretations to test whether a formula is a semantic consequence of a theory. Even more so because a theory may also have infinitely many axioms, as is indeed the case for ZF. That's because ZF includes axiom schemata, which stand for infinite families of axioms. And in fact, one can show that, in contrast to other set theories, ZF is not finitely axiomatizable. And also, there's an even more fundamental issue here, because if you recall, we use the concept of set in the very definition of interpretations, because we said that we have a non-empty set of discourse. And in fact, we also use the concept of set to define what a theory is. So we have already used the concept we purport to be defining with these axioms. And for these reasons, it's not clear how to proceed with only semantic considerations. Nevertheless, we of course are still interested in semantic consequences. We only need a good way to find and verify them. And this is where deductive systems, also called proof systems, come in handy. The main goal of a deductive system is to prove semantic consequences on a purely syntactic basis. So we want to arrive at semantic consequences only by symbolic reasoning, without having to consider all interpretations, or in fact any interpretation. And a proof is a finite sequence of inferences, starting from a set of axioms and using inference rules to obtain theorems. So this leads to a syntactic view of theorems, where we regard as theorems all things we can prove. And so the notion of axiom also arises in the context of proof systems, but here it means logical axioms, that is, usually at least a minimal set of valid sentences that are sufficient to prove all valid sentences. We say that a formula A is a syntactic consequence of a set of formulas gamma if A can be syntactically derived from gamma. So if there is a proof of A from gamma. So this is a syntactic notion of a logical consequence relation. And what we can prove, of course, depends on the proof system. And for predicate logic, and also of course for other logics, there are many deductive systems with different advantages and drawbacks. For example, there are Hilbert-style systems. Such systems are, for example, good for comparing different logics, but not so good for automated reasoning. And one key characteristic of Hilbert-style systems is that they have many axioms and only a small number of inference rules. And I mean a really small number, such as 1 or 2 inference rules. And on the other hand, there are Gentzen-style systems, such as natural deduction, where the goal is to emulate the kind of reasoning that one could call natural reasoning. And this is in fact closely related to lambda calculus by the Curry-Howard isomorphism and sequent calculus. And Gentzen-style systems have more inference rules than Hilbert-style systems. Another important deductive system is called resolution. Resolution is very well suited for automated theorem proving, and Prolog in fact uses specific forms of resolution to derive semantic consequences from programs. So we will discuss resolution in more detail on another occasion, and so on. And the most important property we expect from a deductive system is called soundness. This means that if we derive a syntactic consequence from a set of formulas with the system, then it must also be a semantic consequence of the formulas. And if that's not the case, the system is called unsound. And the converse is called completeness. This means that we can derive all semantic consequences in a purely syntactic manner. So this is of course also a desirable property, because it means that we can really focus on purely syntactic reasoning and need not consider all interpretations. And one property that holds for all the systems I mentioned is called the deduction theorem. This means essentially that if we can prove something, say B, under a specific assumption, say A, then we can also prove that A implies B. And that's a rather important theorem for mathematical proofs, because this gives the formal justification for conditional proofs, where we assume A, then starting from the assumption A, prove B, and then, in a surprising turn of events, conclude that we have proved A implies B. And the deduction theorem shows that this reasoning is indeed justified, at least with the deductive systems I mentioned. And clearly, there's a computational aspect to deductive systems, and in fact there are deep relations between logic and computation. For example, we can use first-order predicate logic to express the semantics of a Turing machine. A Turing machine consists of a set Q of states, an initial state, a final state QF, a tape alphabet gamma, and a transition function delta. And the transition function is a mapping from a state and symbol under the tape head to the next state, a symbol that is written at the current position, and L or R indicating how to move the tape head. And this may seem simple at first, but Turing machines are in fact very powerful. It is widely believed that every mechanical computation can be expressed with Turing machines. So this is very important from a theoretical perspective, because this formalism suffices to express all known computations. For example, everything that a computer can do can also be modeled in this way. And the point is, we can use first-order predicate logic to express what a Turing machine does. And this shows that predicate logic is very expressive and that we can use logic as a formal basis for computation. So here's a brief sketch of how we can do this. First, we can represent tape contents in any direction as terms. And if we have a transition function delta, where, for example, a machine that is in state Q0 and encounters the symbol A goes to state Q1, writes B, and moves the tape head to the right, then we can express this transition as a sentence in predicate logic. So let's use a predicate T with 3 arguments. The predicate T shall be true if and only if the first argument is the current state of the machine. The second argument is the tape content that extends to the left of the tape head. And the third argument is the tape content that extends to the right of the tape head at the current time. So we can express a transition as an implication. If the machine is in state Q0 and so on, then it goes to state Q1 and so on. So this sketches how we can express every computation in predicate logic as a relation between states of a Turing machine, going from one state to the next state and relating the original tape contents to new tape contents. And the rest can also be modeled very easily. For example, we can easily express an initial tape content as a formula and so on. So let's denote with a calligraphic T the conjunction of all formulas that we need to express a given Turing machine Tm. Then results of the computation correspond to semantic consequences of this theory. And we can also construct a formula that expresses the machine reaches its final state, that is, it holds. So in other words, there exists tape content so that the machine reaches the final state Qf. And this sentence is implied by the conjunction of sentences that describe the Turing machine if and only if Tm holds for a given input. And famously, determining whether a Turing machine holds is known to be only semi-decidable. So it follows that there is no algorithm that always terminates and always correctly determines whether a set of first-order sentences is valid. However, as we will see, validity and therefore also unsatisfiability of first-order predicate logic is semi-decidable. This means that there is in fact a procedure that does terminate and answers yes if a given first-order sentence is valid. But in general, every such procedure either yields incorrect results or doesn't terminate if the formula is not valid. And also, we have now seen that predicate logic is really quite expressive and in fact lets us describe all known computations. Now, to conclude, let's briefly consider a few notable properties that hold for classical first-order predicate logic. We have monotonicity of entailment. This means, for example, that if C is a semantic consequence of P, then C remains a semantic consequence of P even if we add another formula A. And this is an important property and worth preserving also when reasoning about Prolog programs, because this means, for example, that when we add a new fact to a Prolog program, then from a semantic perspective, the conclusions that were computed previously are still valid. Then first-order predicate logic is strongly complete. This was first proved by Kurt Gödel in his doctoral thesis in 1929. and this also follows from earlier results obtained by Thoralf-Skolem. And as already mentioned, completeness means that we can prove every semantic consequence of a theory. Now, this direction alone is not very interesting because we could simply introduce an unsound method of proof where we say that everything is provable, and this would then also be the case. So this is only interesting if we can prove not only all semantic consequences, but all and only the semantic consequences. So if we can deduce syntactically precisely the semantic consequences of a theory. And that's indeed the case. There is a sound deductive system with a decidable inference relation such that S is a semantic consequence if and only if S is provable. Of course, not all deductive systems have this property. However, all deductive systems I mentioned are complete. Or, as in the case of resolution, they can at least be made complete with the right choice of parameters. And that's of course nice, because it means that we only need to perform purely syntactic operations to derive semantic consequences. And syntactic operations can be easily automated. So, in first-order logic, we can mechanize logical reasoning by searching for proofs. And of course, as a special case for the empty theory, we can therefore also prove every valid sentence. This is called weak completeness. And this is why validity in first-order predicate logic is semi-decidable. Because if a formula is valid, then there is a proof. So we only have to systematically search for a proof, and if the formula is valid, then due to weak completeness, we will find a proof. An equivalent way to state this is to say that every sentence is either satisfiable or refutable. That is, either it has a model or the negation of the sentence can be proved. Or, phrased more explicitly as a model existence theorem, if a first-order sentence is not refutable, then it has a model. However, validity is of course still only semi-decidable, not decidable. Because if the formula is not valid, we won't find a proof. And at the same time, we may also not be able to refute the formula, because it may be satisfiable. And as we will see, satisfiability is not even semi-decidable, but truly undecidable. And Kurt Gödel is also very famous for his incompleteness theorems. So, which is it? Complete or incomplete? Well, the terminology here is ambiguous. The completeness theorem is about this kind of completeness, which is also called semantic completeness, whereas the incompleteness theorems are results about syntactic completeness and about provability of a system's consistency. So, as a brief aside, syntactic completeness of a system means that for every sentence phi of the system, we can prove either phi or not phi. So in other words, for each statement we can formulate, we get a definite answer, one way or the other. And a syntactically complete system is also called deductively complete, maximally complete, negation complete, or just complete. And syntactic incompleteness is nothing unusual. For example, the empty theory, together with one of the proof systems we mentioned, is incomplete. Or take, for example, the first-order axioms of ZF that we mentioned, together with any of the proof systems that we mentioned. If ZF is consistent, it is incomplete. Because, for example, and as mentioned, ZF doesn't prove the axiom of choice, and also doesn't prove the negation of the axiom of choice. And the same also for other statements, such as the continuum hypothesis, and also for seemingly obvious statements, such as if a set X is smaller in cardinality than another set Y, then X has fewer subsets than Y, which is actually independent of ZF. And Gödel's first incompleteness theorem states that any consistent formal system within which a certain amount of arithmetic can be carried out is incomplete. So, under quite general conditions, a theory is necessarily incomplete. And one way to see this is that as soon as we have a certain amount of arithmetic available, we can already formulate statements about Turing machines and computations in the shape of statements about numbers or sets or geometric objects and so on. And if we had a formal system that can correctly prove or refute all statements we can make about such computations, then we could use the system to answer questions that are known to be undecidable, and therefore such a system can't exist. And we will consider the incompleteness theorems on another occasion. For now, back to our list of properties. The compactness theorem holds for first-order predicate logic. A set of first-order sentences has a model if and only if its every finite subset has a model. So, on the one hand, this implies that if a set of sentences is unsatisfiable, then there is a finite obstacle in them that we can use as a witness of unsatisfiability. And on the other hand, if every finite subset is satisfiable, then the entire theory is also satisfiable. And this is a very important theorem and one of the key theorems that makes resolution work. And in fact, the compactness theorem is equivalent to the completeness theorem. Certainly for well-orderable languages, as we assumed in the above formulation of the completeness theorem, and therefore in particular also for countable languages, which are especially important for our purposes. And then we have the upward and downward Löwenheim-Scullem theorem. This states that when a countable theory has an infinite model, then it has models of all infinite cardinalities. So the downward direction is, if a countable theory has a model, then it has a countable model. And this leads, for example, to Scullem's paradox, because we can formulate and prove from ZF a sentence that states there is a set that is not countable, because ZF proves Cantor's theorem. That is, there is no bijection between a set and its power set. And together with the axiom of power set, ZF proves that there is a set which can't be put in bijection with a set of integers. So on the one hand, ZF proves that there are uncountable sets. However, on the other hand, we know from the downward Löwenheim-Scullem theorem that if ZF has a model, then it also has a countable model. And in such a model, of course, all sets are also countable. So this shows that the notion of countability is relative, because there are sets that are only uncountable from the perspective of specific models of ZF, not from the perspective of all models. And importantly, we have Lindström's theorem. This states that among all logics that satisfy certain regularity conditions, the countable compactness theorem and the downward Löwenheim-Scullem theorem characterize first-order predicate logic as the strongest logic. So, as a consequence, if we want more expressive power from a logic, then we have to sacrifice at least one of these properties. For example, in second-order logic, both theorems fail to hold. And this brings us to the question of expressiveness. How expressive is first-order predicate logic? That is, what can we describe with it? And this question is, of course, central to judge the usefulness of a logic. And we have already seen that first-order predicate logic is quite expressive and can in fact describe all known computations. However, first-order predicate logic can't describe many important mathematical concepts in a categorical way. For example, we can't define the intended model of the real numbers, because due to the Löwenheim-Scullem theorem, we can't control the cardinality of infinite models. So, for instance, if we use a countable first-order theory to specify the real numbers, and the theory has a model, then it also has a countable model, whereas the intended model of the reals isn't countable. Also, we can't define reachability in first-order predicate logic, and here is why. Suppose there is a first-order formula phi of x and y that holds if and only if y is reachable from x, using an edge relation E between two nodes of a graph. Then let's define a certain class of graphs. First of all, we state that every element of the domain is reachable from every element. So, using the hypothetical formula phi, we express that the graph is strongly connected. Second, using the edge relation, we state that for every element x, there is an element y, so that there is a directed edge between x and y. And moreover, we state that for all z, if there is an edge from x to z, then z is equal to that element y. So in other words, we state that each node has out degree 1. And then we state that each node also has in degree 1. So if you think about it, the sentences up to here characterize a cycle graph. That is, a graph that is strongly connected and all nodes have in degree 1 and out degree 1. And in addition, we define a set of formulas ik. And each ik is defined in such a way that it is only true if at least k domain elements are present. So ik states that for all x1 to xk minus 1, there exists an xk that is different from each x1 to xk minus 1. For example, we can take the first 3 axioms and also enforce that there are at least 3 domain elements. And this theory clearly has a model. Take, for example, the directed cycle with 3 nodes. Likewise, there is also a model with 4 domain elements, and also with 5, also with 6 and 7. And it's easy to see that our theory, which describes a cycle graph, has arbitrarily large finite models. And therefore, by the overspill principle, it also has an infinite model. This is a consequence of the compactness theorem, because if we take our theory and add for every natural number n a sentence saying that there are at least n domain elements, and if we know that there are arbitrarily large models, then every finite subset of these sentences is satisfiable. And therefore, by the compactness theorem, there is a model of the entire theory, and that model must have infinite cardinality. So, in our concrete example, we can use the formula phi to describe an infinite cycle. And that leads to a contradiction, because if we start at some node and follow all out degrees, then because the graph is strongly connected, we will visit all nodes. But the node we started from also has in degree 1, so there must be a node in the graph from which we return to where we started. But that means that the graph must be finite. So we must drop an assumption, and the only assumption we made was that phi exists. So we conclude that phi can't exist. So we can't define reachability with a first order formula. And the same also holds, for example, for Hamiltonicity of a graph and the transitive closure of a relation. Also, we can't define the class of finite connected graphs, and also not the natural numbers with only the intended model. Of course, we can state many requirements for natural numbers in first order logic, using, for example, the constant symbol 0 to denote 0 and the unary function symbol s to denote the successor of a natural number. For example, 0 is not the successor of any natural number, and each natural number is either 0 or the successor of a natural number. And if the successors of two numbers are equal, then the numbers are also equal. and x plus 0 is x for all natural numbers, and so on. So we can express many properties we want, but we can't define the intended model with only first-order logic, because no matter what we state, we know that as long as we use only first-order logic, and as long as the theory has an infinite model, there will also be a model that has a non-standard element in it. That is, an element that is different from all natural numbers in the conventional sense. And we can obtain such a model by stating suitable disequalities, as we have just done for reachability. And from the compactness theorem, it follows that the conjunction of all such disequalities has a model. And further, by the upward Löwenheim-Skulem theorem, which is actually a consequence of the compactness theorem, if the theory has an infinite model, then it has models of all greater infinite cardinalities. So the theory will also have an uncountable model, which is of course not what we intend with the natural numbers. And such interpretations are called non-standard interpretations, and we can't rule them out by using only first-order logic. One way to rule them out is to add second-order axioms. This is, for example, done in the Peano axioms of arithmetic. This means that we add a sentence that quantifies over predicates. For example, the so-called induction axiom. And in this way, we can obtain a categorical model of the natural numbers. And also the other things I mentioned can actually be defined in second-order predicate logic. But unfortunately, with second-order predicate logic, we lose important properties, such as semantic completeness. So we can no longer automatically derive or detect all semantic consequences of these theories. So even though first-order logic can express all known computations, it can't express many important mathematical concepts. However, with Prolog, the situation is a bit different, because Prolog is based on first-order predicate logic, but implicitly only considers a particular kind of models, namely least Abraham models. And for this reason, we can actually define many of these things in Prolog and obtain only the intended results. For example, with a single Prolog predicate, we can describe what we mean with natural numbers in such a way that the predicate is true if and only if the argument is a natural number in successor notation. So, considered as a first-order theory, this program consists of two sentences, written in a way that closely corresponds to the syntax of first-order predicate logic, with the convention that variables are implicitly universally quantified. And we can use this predicate to generate and test solutions. And we do this by posting queries, that is, by asking for logical consequences of the theory. For example, let's ask the most general thing we can ask about this predicate, namely, for which x is it the case that the predicate holds? And when we post this, we get a solution, and another, and so on. And each of these solutions is a semantic consequence of the theory, so this holds in all models of the theory. And intuitively, the least Abraham model reflects all information expressed by the program and nothing else. And we can really say the least Abraham model, because one can show that the least Abraham model is unique. And this way to write programs is called declarative, because we describe what holds, and we are interested in what the consequences are. And to reason about the consequences, it doesn't really matter how we arrive at the consequences, as long as the inferences are sound. And a major advantage of declarative programming is that we can reason logically about our programs and ask, for example, why they are too general or too specific. And in fact, we can even write programs that answer these questions and help us to locate mistakes. Another major attraction of declarative programming is that we can comparatively easily delegate a lot of work to the machine. For example, let's look at the definition of natural numbers again. This is very easy to define, and we already get usable results from this definition. And that's a good sign, because especially for more complex programs, we really need all the help we can get to implement them correctly. And it's good if a lot of work can be quickly delegated to a machine.